Welcome, everyone. You know what the symposium is about, what the talk is about, so I don't have to give you the title. So I'm here to introduce our speaker. And also I want to let you know that immediately after this talk, there's then a symposium panel. In fact, I can show. Oh, no. The panel following will have Sarah Cowie, Julian Leslie, Timothy Shan, and Costa Simon speaking. So I invite you and urge you to stay for that. That'll be the hour after Billy's talk itself. So I didn't meet Billy. I was in the presence of Billy when he was at Harvard, and I was visiting Arturo Bozas at the time, who was a graduate student there. And he brought me to a Pigeon Lab meeting, and I'm sitting there. Billy doesn't remember this, but he was there, looking his sort of self. And he was eating, I'm not sure what, it looked like bread, but it wasn't quite bread. And he was cutting it incredibly meticulously and carefully. And I mean, I just thought him a bit weird then. Little did I know. So I wanted to show a picture of him, sort of an earlier incarnation, and I went online, doing Google, of course, and so looking for Billy Baum in his younger years, and what I came up with, that is Billy Baum dressed as a cardinal at St. Peter's School. The interesting thing is that Billy Baum, who I thought might be Billy for Halloween or something, turned out to become the longest serving cardinal in U.S. church history. And I still thought this might be Billy wearing a yarmulke, because that's his heritage. But then found out that no, I had the wrong picture. Some brief biographical details. You know, he did his undergraduate and graduate work at Harvard, did a postdoc at the other Cambridge, then was on faculty at Harvard for several years, then moved to New Hampshire to be with Tony Nevin. He took a sabbatical while he was at New Hampshire in San Francisco, and after spending the sabbatical there, he went back to New Hampshire and decided to retire early to leave the beautiful cold and snow of New England for a city about, you probably know Mark Twain's famous line. Mark Twain was from Hannibal, Missouri, and I'm now at Washington University in St. Louis, so everything comes together. Mark Twain said, you know, in his usual hyperbole, the coldest winter I ever spent was a summer in San Francisco. But remember, Twain also said, I fell in love with the most cordial and sociable city in the Union. After the sagebrush and alkali deserts of Washoe, San Francisco was paradise to me. I think the latter probably best represents Billy's feelings and the reason for his move to San Francisco. Billy's made seminal contributions to the empirical and conceptual foundations of behavior and to behavior analysis. And I guess I would offer the comment that much of his work needs absolutely no introduction. And I would dare go on to say that if there's any student in the audience here, any graduate student in the audience here, who's not familiar with a reasonable amount of Billy's work, I actually would say consider transferring to another program, and also let me know so I can let ABA know that they should reconsider accreditation. A select quick overview of some of Billy's work. I'm showing you some abstracts. Here we have work that he did with some of his students, Carlos Aparicio, John Kraft, Costa Simon, who's a speaker in the next session. And then there's work with colleague Michael Davison down in New Zealand, Many of you will be familiar with that work. And then, of course, the work he did with Howie Racklin. They were graduate students together at Harvard. And then incredibly seminal work on correlation-based law of effect, the generalized matching law, bias and under and overmatching. One of my favorites, it's a nice brief article, Choice in Free-Ranging Wild Pigeons, a science article that I recommend reading. It's lovely. It's really cool. And then his more conceptual, theoretical research that you're going to hear some about, molar behaviorism. Here is well-known, highly respected book. You'll notice the subtitle on the book changed from the first edition to the third edition, in case you weren't aware. It changed from the first to the second, and then kept the new one on the third. Then it was, it's been translated to several languages. I wanted to show, I was showing this to my wife, and I said, oh, here's the Portuguese edition. She immediately said, no, it's not, it's the Brazilian edition. She didn't say that positively. She's from Portugal. And then, if you want to get basically know all a large amount of the research he's published, his Science and Philosophy of Behavior, the Selected Papers book, which has comments on each of the papers that he wrote, so you really get a full sense of what's going on. I mentioned his work with Howie Racklin. It's a very close relationship, and I think it really marks the Kafka line, for some of you prefer the Aristotle line, about the whole is other than the sum of its parts, or the whole is greater than the sum of its parts. And I think in the case of Billy and Howie, that's true. And if you'll indulge me just for 10 seconds, I just want to show a picture that included me. So, so there's Carlos Aparicio, me, Howie Racklin, my daughter and wife, and then Billy. So they're personally important to me. So and this was at an Albany. So let me ask you to join me in welcoming Billy, and I'd like you to sit back and, for many of you, get to rethink much of what you thought or were taught about reinforcement and behavior. So I give you William Baum.
Well, thank you, Len. I want to share with you today a comprehensive conceptual framework for thinking about behavior. And everything I'm going to say stems from evolutionary theory. So, first I'm going to talk about what is behavior and how to measure it. And I'm going to tell you that behavior is continuous. A good way to think about it is that it's flow. Behavior is process from an ontological point of view. And that leads us to what I call the Law of Allocation, which I will say applies at any time scale. And then I'm going to talk about how to explain the behavior that occurs. And I'm going to emphasize the function of behavior, which ultimately is reproducing. But that will get us to the concept of a phylogenetically important event, PIE. An event that's important phylogenetically is one that impacts fitness or reproductive success. And that will lead us to the concept of induction and the concept of covariance, which accounts for adaptation behavior. So behavior is process from an ontological point of view. Process is change or action through time. And you could think of behavior as flow. But the important idea to have here is that behavior takes time. Behavior takes time. So to measure behavior, we measure time. And the other point that is key is that behavior is continuous, because an organism that is alive is always behaving. And that means that the activities of an organism always take up all the time available. Now, on top of that, time is limited, right? There are only 24 hours in a day. So what that means ultimately is that activities must compete for time. And this insight is really fundamental to what I want to say. So just to illustrate here, on the left here, we have 4 activities and a timeline. Whenever the trace is up, the activity is occurring, and the activities are gaining resources, socializing, maintaining health, and spending time with family. And this is a record over 4 days, and you can see that the activities are episodic. But we can summarize what happens over these 4 days in the form of a pie chart, like on the right. And you can see that maintaining health takes up the most time, and after that is gaining resources and spending time with the family, and then socializing. So this is a way of looking at the allocation of time among activities. And if conditions change, this allocation will change. So you get a different job, or you get divorced, or married, and have a child, or whatever, and the allocation changes. Now here are some actual data. Those were hypothetical. These are actual data. 2015 US civilians, and the blue that takes up the most time is maintaining health, because it includes sleeping. You know, we sleep for about 1/3 of the time. So that's a big one, and then the RES is gaining resources, and the red is reproductive activities, and the little yellow one in there is relationships. There's a tiny black sliver of ones that couldn't fit anywhere. Then I took the time devoted to gaining resources, and I broke that out into its parts, which also are activities. And the main one is working, the yellow, and after that is eating, that's the purple. The dark gray is buying things, shopping you could say, and the light gray is educational activities. So, every creature in the world is on a time budget, and that's what we're really talking about here. I call this the Law of Allocation, which says that the time spent in any activity, we'll represent that as B sub I, relative to the total time of all activities, the sum of B, is equal to the relative competitive weight of that activity relative to the sum of all the competitive weights of all the other activities. So V stands for competitive weight, has been talked about in some different ways, as consequences, as reinforcers, but I'm going to talk about it as induction. To me, competitive weight is the result of induction. But the intuitive part of this, the part that you should grasp right away, is that the more competitive weight of an activity, the more time it takes up. So that's the general law of, it used to be called the generalized law, generalized matching law, but I like to call it the law of allocation. And I want to emphasize that this law of allocation applies at any time scale. Sometimes people get confused and they say, well, this only applies at some very long time scale. But no, that's not at all what's intended. Some activities take longer than others. This is a fact of life. It takes less time to read a chapter in a book than to read the whole book. It takes less time to kiss someone than to love someone. It takes less time to avow a belief than to believe the belief. In all of these examples, you have a shorter time scale activity that is part of a longer time scale activity. And so the relation between them is a part-whole relation. For those of you who like big words, that's mereological. A mereological relation. But it's a part-whole relation, and the shorter scale part fits into the longer scale part, right? And so all the parts sum to the time taken by the whole. Now, because there's always a time limit, the parts of any activity compete for time. Now, this can be on any time scale. So, like, for example, someone practicing ballet, the parts of a ballet step, say, moving the hand, moving the arm, moving the leg in a certain way, that's on a scale of milliseconds, if not less. And the parts of what we're all probably familiar with, time management, those are activities that are on a large time scale. So I want to dispel any idea you have that this doesn't apply at small time scales. And here, just to drive this home, is another diagram showing nesting of activities. There are 4 activities on the left: professional activities, householding activities, personal activities, and activities with friends, socializing. Now, if you take any one of those, remember I did this before, take any one of those activities and break it out into its parts, and in the middle there you see the parts of what I call personal activities, and they are things like maintaining health, reading, meditating, cooking, working on the car. Of course, these will vary from person to person, but the point is that you can take any activity and you can break it out into its parts. Meditating has parts like breathing and chanting and focusing. And the insight to have here is that as you go from left to right in this diagram, you go from longer to shorter time scale. Now, the law of induction is, I want to say something. In case you don't notice, I'll say it now. I'm going to be presenting you behavior analysis without the concept of reinforcement. So the law of induction says that activities are induced by phylogenetically important events. And what that implies is that induction is a fundamental feature of organisms. And so why should it be this way? Why do these important, phylogenetically important events, PIE, why did they induce behavior? Well, to answer that, we have to first look at what organisms are good for. This comes right out of evolutionary theory, the function of an organism. Well, a good way of thinking about this is to think of an organism as an interactor, that's David Hull's term, carrying about a replicator, okay? Now, the replicator is the thing that is copied. And the interactor interacts with the environment. The interactor has lots of advantages. It provides protection for the DNA, defense, immunity against bacteria and viruses, these less organized life forms that we constantly have to deal with. And it provides physiological mechanisms for this, and also behavior. So the general story here is that organism-making genes, the genes that would make an organism, are selected because they offer these advantages, and that translates into more faithful copies of the DNA and offspring. Now, something happened to this slide, but here's the summary is this. The organism is DNA's way of making more DNA. That's the function of the organism. And so it shouldn't surprise you if we look at organisms this way, as the replicator carrying about the DNA, to understand that this is its function. And so ultimately, whatever we're going to say about organisms, it comes down to reproducing. So behavior has this ultimate function, reproducing. And the great advantage of behavior is that it deals with events that might affect the likelihood of reproducing. Right? Might either threaten it or enhance the likelihood. And these are what I'm calling phylogenetically important events. And they're things like a potential mate, or prey, or a predator. So clearly there can be good PIEs which tend to enhance reproductive success, and there are bad PIEs which tend to threaten reproductive success. So the PIEs induce activities that ultimately serve reproducing. So encountering a mate induces courtship, encountering prey induces capturing and eating the prey, and of course encountering a predator induces hiding or fleeing from the predator. So you get the picture. These are some examples. Potential mate. Offspring, of course, are PIEs. And humans eat all kinds of things which are PIEs. Other species, other prey. But also things like water and nesting site. These are PIEs. On the flip side, fitness-threatening PIs are things like injury. These are to be avoided. You see the little boy snapping up the helmet down there. These are to be avoided. Predator, toxic organism. In our species, which is a highly social species, we have lots of social PIEs. things like smiling and laughing, right? These signal accord, you know, I'm with you, kind of. But then, of course, there's the reverse of that, PIEs that signal lack of accord. And then there's imitation. We should never leave out imitation. This is clearly a case of in induction where a model induces behavior in an observer. So the advantage of behavior is that it, remember, is, you know, the interactor we're talking about. The advantage of behavior is that it serves to change the environment in ways that promote reproductive success. So it acts to mitigate bad PIEs, you know, like activities like hiding, fleeing, defending, and enhance good PIEs, like mating and courting a mate, foraging, and protecting offspring. Now, the insight to have here is that this induction is due to natural selection. If there were, imagine a population in which some of the individuals don't behave these ways, that induction fails, let's say, in the face of a predator, they don't act effectively, that individual is going to leave fewer offspring. So you're going to wind up with a population where all the individuals respond vigorously to predators, to prey, to potential mates, and so on, because of natural selection. But we also need to talk about how behavior works in ontogeny. That is, how it is that an organism adapts to an environment within its lifetime. And for that, we have the law of covariance. Now, induction is determined in one way or another by environmental covariance. Now, covariance operates on the scale of phylogeny across many, many generations within a population. And so if you have some sort of a behavioral trait, let's say, that covaries with fitness, with reproductive success, then that trait will tend to be selected and will appear in individuals in that population just as a result of phylogeny. So, you know, this is reliable kind of activities that you see. For example, a female bird flying into a male's territory, he begins to court her. And that's a result of natural selection. But it's also true that within an organism's lifetime, covariance determines induction. So you may have come across the concept of phenotypic plasticity, and behavioral plasticity is an example of that. And that is what we consider adaptation in an organism's lifetime. And it is an additional advantage that interactors confer. I don't use the word learning, it's too vague, it doesn't help us. So I'm only going to talk about sensitivity to covariance or correlations. I'll use those two terms interchangeably, but I prefer covariance because correlation has too much baggage. So organisms are sensitive to covariance in the environment. For example, if a certain location covaries with the occurrence of prey, then that location will induce approach. The organism will visit it. But if a location covaries with the presence of predators, then that location will be avoided, so the location will induce avoidance or visiting other locations. All of this, I want to emphasize, is occurring on average and in the long run, just like with evolution on due to natural selection. Not every occasion is successful. It's only necessary that the probability of success, the likelihood of success on across occasions is greater than the likelihood of failure. That's the basis of selection, and it's the basis for covariance to select which behavior. So let's consider this now. There's two kinds of covariance that will account for adaptation. One is covariance between some feature of the environment, like what we call a stimulus, and a PIE, right? So what happens there, let's say you pair a tone with food, or a key light with food produced by pecking, that stimulus, that feature of the environment will now induce that activity, which we consider to be the result of, in some Pavlovian terms, a conditional stimulus, a discriminative stimulus. But the point is that that environmental feature will now induce the activity. And the second kind of covariance is covariance between an activity and a PIE. Well, you're all familiar with setting contingencies, and so if you set a contingency, you create a covariance. And then that results in the phylogenetically important event induces that activity. Because that activity we call operant activity. So the PIE, or its proxy, a stimulus, induces an activity, and the activities, remember I said, they function to change the environment. So the PIE induces activity, which we call operant activity, that changes the environment in some way. But take an example. Pigeons pecking. Now you can induce pecking in a pigeon just by presenting food occasionally. And so you can get food-induced pecking. But if you arrange that pecks at a key produce the food that induces the pecking, then you get operant pecking at the key. And then, of course, you can train that pecks at a red key produce food, pecks at a green key do not, and lo and behold, the red key induces pecking and the green key does not. In an everyday example, if you encounter a potential mate that may well induce sexual arousal, that's the result of phylogeny. But there's operant behavior about potential mates, and we call that dating. And of course, there are rules about dating. That's the discriminative part. And they're mostly about coercion avoidance. So that parallels the example with pigeon pecking. So here's the first kind of covariance between a signal and a PIE that results in what I'll call a conditional inducer. And this covariance can either be positive or negative, and I've drawn here a simple diagram. Positive means that when this signal is absent, the rate of the PIE is very low. When the signal is present, the rate of the PIE is high. The opposite is negative covariance, in which when the signal is absent, the rate of the PIE is high, and when the signal is present, the rate of the PIE is low. So examples are on the right here. Positive covariance, a warning of predator, parasites, and illness, money and food and other goods, a gun and injury. Those are all positive covariance. Negative covariance, things like the distance of a predator and the likelihood of being attacked, parasites and the likelihood of mating, and of course, winter and the likelihood of food. Now, the simplest form of covariance is just pairing. Right? And you can see here, it looks like the elephant should be very careful next time in approaching the water hole. Not just the elephant, however, the crocodile also might have some pause. But more complex stimulus PIE covariance is something like recognizing a person from a picture. And the teacher here is saying, Mrs. Hammond, I'd know you anywhere from little Billy's portrait of you. So here's a way of diagramming some of this. On the left, the diagram on the left, what you see here, the E is the environment. It provides a PIE, impinges on the organism O, and so the PIE induces some behavior, which I show up there as B. Some of it is B sub O. There are various activities. Anyone who's done some experiments will know this. These are adjunctive activities induced by, let's say, food. And now, if you take one of those induced activities and you make a contingency so that that activity now covaries with, let's say, the food, right? So that activity produces the food, but the food induces that activity. And those others, notice, they haven't gone away. But you've closed the loop. And so the activity produces the food induces the activity, and so on, round in a loop. And an interesting thing about this is, if you think about it, it collapses antecedent and consequence. No longer is that a meaningful distinction, really. You have to think about time a bit differently if you're going to think this way. And the second kind of covariance between an activity and a PIE, also positive and negative. So the activity rate on an A here, this doesn't really do it, does it? Okay, the activity rate anyway varies directly with the PIE rate varies directly with the activity rate. It can be a linear relation, it can be a curvilinear relation, and some of you will recognize that as For example, ratio schedules and interval schedules. And on the right, negative covariance, again, can be a line or can be curved, but it means that the more of the activity, the lower is the PIE rate. That's like in avoidance. And so here's a way of diagramming the maintaining of behavior. On the left, obtaining. So the red arrows are showing you covariance, and the black arrows, the red arrows have two heads on them, and the black arrows are showing you induction. So they have some sort of signal or context. It induces the activity. The activity covaries with the PIE, but so also does the signal. So they both induce the activity. Both the signal and the PIE induce that activity and keep it going. On the right is avoiding, and notice it's exactly the same except for one thing, and that is I drew a line through the double arrow going from the behavior to the PIE because that's a negative relation, right? That's negative covariance there. But the point is that, say, PIE is, we're often in the laboratory, it's electric shock. The electric shock induces the activity which avoids it. And the signal induces that activity as well. So that's a way of diagramming this to a certain that has, at least simplifies it. So we have two laws that explain allocation and the change of allocation. One, and they really work together. Induction, the PIEs and their proxies, induce activities, both non-operant and operant activities. And we have covariance, which selects activities. Particularly covariance, we're talking here about covariance between an activity and a PIE. Now here I've included this slide because I want you to see right out front how much greater the explanatory power of induction is relative to reinforcement. Induction explains operant and respondent conditioning, straightforward. It explains operant and adjunctive activities, and explains all these without any hypothetical constructs. Right? No concept of strength, whatever that is. If you wanted to retain the term reinforcement, it would just refer to the increase in operant activity. It's nothing more than that. Induction supplies a mechanism for stimulus control. When I was in school, and Skinner, would say, discriminative stimulus sets the occasion for the response to be reinforced. Well, yeah, but that's not an explanation. That's just a description of what happens. How is it that the discriminative stimulus actually affects behavior? And the answer is induction. It solves the problem of the first instance. The behavior has to occur before it can be reinforced, right? Well, induction takes care of that. The first instance is induced, and then, of course, you can have covariance. And finally, it explains avoidance, which reinforcement theory never, ever plausibly explained. And if you tell me, oh, what about two-factor theory? I'll tell you, you're telling me fairy tales. The other thing is that it provides a coherent explanation for activity rates on ratio and interval schedules, which I don't have time to go into now. So here's what I've told you. I've told you there are three laws. The law of allocation that tells you what to measure. I told you that behavior is a continuous flow, that activities are extended in time, and therefore activities compete for time. And this is how you can measure behavior as relative time at any time scale. I told you about induction, which used to be talked about as consequences, but induction due to phylogeny and the way it works in ontogeny, due to phylogenetically important events that induce activities. And the induced activities, mind you, they include operant activities. And finally, I talked about covariance, which allows adaptation to a changing environment. So I talked about behavior PIE covariance, which leads to operant activity, and signal PIE covariance, which leads to what we have in the past called stimulus control. And now I will plug my books. This one on the left is just out and is for sale. Len showed it to you. It's for sale in the bookstore. It's a collection of papers with my commentary. And the one on the right is my idea for an introductory book. And it's coming out later this year. They tell me that the proofs are coming at the beginning of August. So that is another book that I'll plug. And I thank you for your attention.